well known for his work on graph homomorphisms and dichotomy theorems, and he works in the border of graph theory and algorithms. He's also the managing editor of the International Journal of Graph Theory, and today he's going to talk about his personal perspective on a dichotomy theorem which he has seen from conception to settlement. Over to Paul.
Thank you. I'm very honored to be invited to give this guest lecture at the Ramanjuram Hall, as well as be closing a feature of the conference, the wonderful conference that Venkatesh and Matthew and Saket organized. This is a general talk. No background is assumed. So at least those of you who are here for the conference might be bored at moments, but I hope I have livened it enough by history, recollections, and my personal memories of how all this happened. So, okay. Right, now my clicker has lost itself. I'll try to turn it off and on again. In the meantime, before we get to this, I want to say that I will start from the beginning. So, you probably all know, whatever field you come from, that in the 1930s, mathematicians, especially logicians, try to formulate a formal version of what an algorithm is so they can decide, tell whether problems can be solved algorithmically or not. And these people came up with various different models, but it turned out that they are all equivalent in the class of problems that they consider solvable by algorithms. And when we talk about functions, we talk about computable, not computable, and we talk about problems, we talk about solvable and unsolvable, but we'll be talking about decision problems, and the standard terminology there is decidable and undecidable. And so let me bring in graph theory right away. Let me give you a couple of examples. And these are standard problems for people in graph theory, or at least the first one is, and that's graph coloring. I have a graph and I want to assign colors to the vertices so that adjacent vertices have different colors. And in this case, let's just say we want to use three colors, red, blue, and green. And this is clearly a decidable problem. It's a finite problem. You can figure out any algorithm you like. But for future reference, let me introduce a particular kind of algorithm. I will simply start listing all possible assignments of the three colors, 3 to the n assignments I can imagine of three colors to the vertices of this graph. So I'll go through them, and at each stage I will start checking whether whatever edge I pick, it's true that the ends of the vertices have different colors. And so here it's not true, so I check something else. Eventually I come to one that works, and I declare this is the coloring, or I decide it's not possible. So this is a decidable problem. Here is another problem. This is an example of an undecidable problem. So if you look at this graph, you'll see that at every vertex, the neighbors induce a path with three edges. So if I fix this vertex, the neighbors form a path with three edges, or four vertices. This is true for the outer vertices, but notice it's also true for the inner vertices. So we can say that this graph realizes a path of length 3 in its neighborhood. And you can ask, if I give you a graph G, is there a graph H which realizes it? All neighborhoods of which are isomorphic to G. This turns out to be undecidable problem. So the first problem we looked at was decidable. The second one is actually provably undecidable. You can reduce one of the well-known undecidable problems to it. I think tiling the plane or something. This is a nice problem, by the way, to play with if you want to pass time in a boring lecture. You can try to construct, say, a graph in which every neighborhood is a path of length 5. It's pretty tricky. Path of length 2 is not possible, and so on. All right, so once we had problems which are decidable and undecidable, the next stage of history was those that are decidable. Is any algorithm good, or what does it mean that they are efficiently decidable? And two people proposed an answer at roughly the same time. One was a logician, Cobham, and the other was a graph theorist, combinatorial optimization person, Jack Edmonds. And they came up with the same definition. They decided that, for various reasons, that what should be the division between tractable and intractable problem is whether there is an algorithm that takes a number of steps that is proportional to a polynomial in the length of the input. So this is the distinction we use to this day. And it divides the decidable problems to tractable and intractable. By the way, Edmonds decided this, or put it in the paper in which he solves the matching problem. So for those of you who are not at the conference, here is an example of a matching. It has two edges, but there are some vertices which are not covered by the matching, so this is not a perfect matching. There is another one which is perfect, covers every vertex. And to get from this one to that one, you only have to notice that to cover this vertex, I'd like to make this a matching edge, so I must make this a not matching edge. I can make this a matching edge, and that's how I go from here to here. And this method of augmenting paths was first observed by Claude Berge. And he used to say that when he made this observation that if a matching can be improved, it can be improved along an augmenting path, he thought he solved the matching problem. Because now basically all you have to do is look for an augmenting path. And it wasn't until Jack Edmonds that he realized, well, this is not so simple. In fact, there are complications in seeking augmenting paths. And he had a complicated method of the Blossom algorithm. This is the 60s now, right? Those of you who lived the 60s, I don't see that many, will remember the time of the hippies and the war marches and so on. Jack's paper was called On Paths, Trees and Flowers. So I was a sign of the time. All right, so we have seen a couple of examples already. The perfect matching problem is not only decidable, it's actually tractable. That algorithm of Jack, the Blossom algorithm, is polynomial time. How about the other problem? The coloring with three colors? We still don't know. That problem is still not completely sure. We think it's not tractable, but we don't know. So, are there intractable problems in this strict definition? Problems that cannot be solved in polynomial time? By this time, it was late 60s, early 70s. Hartmanis and Stearns, in their well-known paper about something else, constructed some artificial examples that are provably not polynomially solvable. And then a few years later, there was a bunch of papers. This is one where some well-known problems from logic, automata theory, and so on were shown to be intractable. But they're not problems that graph theorists were particularly interested in or that entered the consciousness at the time. all these provably intractable problems had something interesting in common, and that was, in terms of the algorithm we have seen about coloring, it was the second stage that was intractable. Even if you already guessed what the colors should be and were just checking whether it works, even that was provably not polynomial. And you know, all the problems typified by tree coloring, all the problems graph theorists and optimizers are interested in, don't have that property. Once you guess a solution, you can verify in polynomial time that it is or it is not a solution. So this was kind of a mismatch, and this mismatch is still today, valid today. So this was the stage at which Steve Cook wrote his breakthrough paper, in which he accomplished several things. One was he defined the class NP. This is the class of problems which, when you have a proposed solution, you can verify in polynomial time that it is indeed a solution. He formulated it in terms of non-deterministic computation, where you imagine that you are simultaneously pursuing all the candidates and you're only checking whether it works. So this is the class NP. All problems that can be verified in polynomial time. He also emphasized the importance of polynomial reductions, polynomial time reductions. If you can solve this problem in polynomial time, then you can use it as a subroutine in some other problem and solve that in polynomial time. So you reduce one problem to another. There were reductions in the literature before, but he's kind of systematically used it to investigate the class NP. And lastly, the third major contribution was that he introduced or emphasized the satisfiability problem, in which you have a formula in conjunctive normal form, and you're asking if there is a satisfying truth assignment. And so he proved if this problem could be solved in polynomial time, then all the problems in NP could be solved. And this was really a major paper. He gave a couple of lectures about it. Karp was in one of them, and he realized that the Earth has moved, something earth-shaking has happened, and he made it somehow his task to make this well known. He wrote this second paper that we always cite about NP completeness, in which he translated this maybe obscure logic paper into mainstream computer science. He proved all these other problems, the problems we are always interested in, are themselves as useful as SAT for the reductions. So if any of them is polynomial, then NP, all problems in NP are polynomial. And he also actively traveled to promote this fact, this knowledge. So there was a meeting at IBM Watson Institute in '72, in which he spoke and invited a few other people and propagated this idea. There was another meeting, I think, in Montana in '73. And in '74, there was an American Math Society meeting in San Francisco, in which he organized a session called Perceptorial Introduction to Computer Science for Mathematicians. And I was fortunate enough to be at that. So this is where I became fascinated by this topic. I have just gotten my PhD a couple of years earlier, and I was a postdoc at Simon Fraser University. My advisor was a well-known logician by the name of Alistair Lachlan. And Alistair and I flew down, and Alistair was busy in some other sessions, and I attended this. And then on the way home, we sat together on the plane, and I was excitedly telling him this great news, and he listened politely. But he also, I saw something was bothering him. And then when we landed and we were about to say goodbye, he said, "You know, this is weird. Why would there be in this new logic class NP, only problems that are as hard as anything and as easy as anything. There is only NP complete and polynomial. You never mentioned anything else. And I had no answer to that. I thought, okay, he's right. There's this big class and there is only the hardest and the easiest problems. Well, here, Alistair had a student, PhD student, and a few years later, that student actually proved that if P is not equal to NP, then there are problems of intermediate complexities. In fact, there is an entire hierarchy of those, and this is what we now know as Labner's theorem. Now, I am presenting this from a personal perspective. I don't know whether Alistair would say that it was our discussion that made him ask Richard to do this. Probably not. But, you know, that's how I remember how this happened. And then another milestone that we have to mention after that is, of course, the book of Gary and Johnson in '79, which I think is the most cited work in computer science. Has some, I don't know, 25,000 citations, and it still continues to be the Bible of NP completeness. Now, this is where I had another lucky strike. Both Gary and Johnson were at Bell Labs, and next to Bell Labs is a university in New Jersey called Rutgers University. And by this time I was an freshly hired assistant professor at Rutgers University when David Johnson came and gave a seminar. This is 1976 or 7, kind of thinking about this book and wanting to practice how this would be taught. And I took that class, or audited that class. And there was really a wonderful introduction to it from the horse's mouth. And that also influenced me greatly in my interests. I was in mathematics department at the time, and this is what made me kind of shift more into computer science. That mathematics department, by the way, if anyone happens to be from math, at that time was the center of activity in the drive to classify finite simple groups. The chair of the department was Danny Gorenstein, who eventually became the leader of this effort and wrote books about it and so on. So math department wasn't uninteresting as well. But I sat in this lecture in computer science. All right, now we're coming to 1978. By this time, graph theorists were already interested in NP completeness, and it was already beginning to be somewhat questionable if you wrote a paper that had nothing else in it than NP completeness, right? It was beginning to be frowned on because there was so much of this, and this is NP complete, and that is NP complete. So I was surprised when in '78 our paper on basically NP completeness got accepted in Stock that year. And then I looked at the other papers that were accepted. There was actually a number of, I found just quickly looking, 5 that had a similar flavor of proving NP completeness, not for one problem, but for a family of problems. And so there are different problems. I won't spend time describing all of them. Let me just tell you what was in our paper. So we said, in the matching problem, you're trying to pack as many disjoint copies of a single edge as possible, and that we have a polynomial algorithm. What if you want to pack triangles or pentagons or some other graph? And so we classify these problems. If what you're trying to pack is a union of edges and single vertices, then the polynomial algorithm that basically uses matching. Anything else is NP complete. So the other paper also have similar flavor, and I will talk about the Schaefer paper next, which plays a star role in this history. But all the others had either complete classification or at least discussed a family of problems. And I think somehow the Stock Committee that year liked this idea and chose all our papers. So let's talk about Schaefer. Schaefer was a student of Karp, and he was trying to come up with more tools to use for proving NP completeness, because satisfiability with clauses of size 3 was so useful for the NP completeness theory. Maybe there are other similar satisfiability problems that there could be, and he wanted systematically to examine all of them. So he developed the following model. I will illustrate the model by translating 1 in 3 SAT. 1 in 3 SAT is the problem in which clauses don't have negated variables. There are clauses of size 3, no variable is negated, and you want in each clause to be exactly one variable to be true and the other 2 false. This is a well-known NP-complete problem we use a lot nowadays, but actually came from Schaefer. So Schaefer would view this problem as follows. He would introduce a ternary relation on the set 0, 1, which has the triples that have exactly 1, 1 in every possible way. And then he would say what we are looking for is an assignment from the variables to the truth values, so that the triples, so that we have ternary relation on the instance as well, right? The triples are in the relation, and anything which is in the relation should be mapped to a triple which is in the relation. So out of any 3 variables, the values will be either 0, 0, 1, or 0, 1, 0, or 1, 0, 0. Okay? So this is the problem 1 in 3 SAT. Let's look at 2 SAT. Let's formulate 2 SAT in this language. Well, 2 SAT has the complication that there are negated variables. So I no longer have just 1 binary relation, but I will have 3 binary relations. The first one will correspond to pairs of two clauses which don't have any variable negated. It's allowed that the variables have values false, true, true, false, or true, true. Those are the 3 pairs of values that the variables in an unnegated clause can be. If the first variable is negated, then I just change those first bits to the opposites. And if both variables are negated, then I flip all the bits. What if the second variable is negated? Well, the clauses are symmetric. You just flip them, and then you use one of these relations. So, for example, suppose we have 2 clauses, x or z, and x or y bar. So we put xz in the relation R0. We want the values to be these. And then we put yx, we flip them in the relation R1. Their values should be these. I think you get the idea. So the general SAT problem is the following. You have a finite set of finitary relations on the ground set 0, 1. And then the input is a set with a corresponding set of relations. By that I mean if S has 1 ternary and 1 quaternary relation, or 2 quaternary relations, S1, S2, S3, then the input will have the same 1 ternary and 2 quaternary relations, R1, R2, R3. Anything in R1 will map to anything to S1, and so on. Well, Schaefer actually classified in his paper the complexity of all these problems. So there are some situations that are polynomial time solvable. The first 2 are the trivial situations in which the all 1 vector or the all 0 vector satisfies all the relations on the set 0, 1. So that means this is trivially, any instance is trivially a yes instance because I make all variables true. In this case, they satisfy all the constraints, or all variables false in this constraint. Now you also know that 2 SAT is polynomially solvable, and the solution there is essentially propagation. If this is true and there is such and such clause, then that must be true or false or whatever. And by propagating in a suitable way, you can solve 2 SAT. Now the other 2 Horn clauses and cohorn clauses are also solved by propagation. Those are satisfiability problems in which you have at most one unnegated variable. So are equivalent to problems that have at most one negated or at most one unnegated variables. So all these three classes are solved by propagation. And the last class is different. If your relations can be expressed by equations modulo 2, then you can use algebra, you can use Gaussian elimination or whatever to solve this system of linear equations. These are not solvable by propagation. This is all very different from the others. This difference permeates this whole theory. But actually these are all known, so this wasn't Schaeffer's contribution. What Schaeffer accomplished was that he proved that all the other problems are NP-complete. Okay, so here is the dichotomy. All these are polynomial, and all the other ones are NP-complete. Okay, what is the situation, what's happening in the meantime in graph theory? Well, graph theory had its own dichotomy that goes back to Karp. We know that two-coloring has a polynomial algorithm, which is essentially propagation. If you color me by A, then you must color my neighbors by B, and then their neighbors by A, and so on. And if that doesn't work, then it's not possible. Karp proved that if K is at least 3, then the K coloring problem is NP-complete. So this is a prototype dichotomy. This was extended in graph theory in many different ways. For example, multicolorings. In multicolorings, you are assigning to a vertex not one color, but a t-tuple of colors. And adjacent vertices must receive disjoint t-tuples. So here is the t-tuple K coloring problem. Given a graph G, is there a t-tuple K coloring of G? And this is a result of Irving, 1983. If T is too big with respect to K, bigger than half of, or at least half of K, then either you don't have disjoint tuples, or every tuple has a unique opposite tuple. And in those trivial problems, the problem is a polynomial, and in all other cases, the problem is NP-complete. So you feel this is kind of similar to the ordinary coloring, and in fact, it extends the dichotomy. But to describe the most useful and general extension of these questions, let me remind you of what a homomorphism is. If we have two graphs G and H, then a mapping of vertices that preserves adjacency in this sense is called a homomorphism. And there is a homomorphism problem. For each fixed graph H, there is a homomorphism problem. Given a graph G, is there a homomorphism to this fixed H? So for example, if the fixed graph H is a complete graph, then we are talking about K coloring, because preserving adjacency means mapping adjacent vertices to different colors. And this is the graph that obtained on the set of all t-tuples on K element, t-tuples of K elements, by having them adjacent if they're disjoint. This is the Kneser graph on T and K. So the homomorphism problem for the Kneser graph is the t-tuple K coloring problem. So the two dichotomies that I have cited are special dichotomies for the homomorphism problem. And so in maybe late 80s, Neschetzer and I have proved a dichotomy for undirected graphs, which says if the graph H is bipartite or has a loop, in which case the polynomiality is kind of easy, these problems are polynomial, and in all other cases are NP-complete. So this is a dichotomy for homomorphism problems, which includes the two specialized dichotomies that I have shown you, as well as a number of other results on dichotomies. Now, Neshetsill came to Vancouver in 1988 for a sabbatical. We picked up a number of problems to work on, but eventually this consumed all of our time. He was renting the basement in my house, and we worked at school, and then we got home and we worked at home. And then sabbatical was over and he went home, and we still continued writing, trying to solve this. We're convinced that we could do it, and it turned out to be really difficult. And so then in the end, when we had it, I felt, God, I hope this wasn't wasted 2 years, you know. This is a thing you devote so much time and effort. The paper had, I don't know, some 40 pages. And luckily, that didn't turn out to be the case. It's our most cited paper, both for Neshetsill and for myself. I should actually move to cite our paper. It's only came out in 1990. It turned out to be important in a way that I will describe in the rest of the talk, but I just wanted to say that many new proofs have appeared since that use universal algebra or dynamical systems and probability measures and other high-power techniques, but all these proofs are still difficult, or at least deep proofs, complicated proofs. Anyway, the reason the result turned out to be interesting and we were recognized for it goes to Thomas Feder, who was a student of Donald Knuth at Stanford, and a common friend passed him our paper. And that was the time Thomas was studying the paper of Schaefer, and so he put the two papers side by side and started comparing them. And he said, okay, so we have here an arbitrary set, and here we have a very special set. And here we have a very special relation, and here we have arbitrary relations. But otherwise, in both cases, we are talking about preserving relations. We have inputs with corresponding relations and mappings that preserve all relations. And then here there was a dichotomy in which the first case here, answer is always yes, because a constant mapping to the vertex with the loop is a homomorphism. And here the answer is always yes, because a constant assignment of truth values yes or truth values no satisfies all constraints. And then there was a situation in which the algorithm is a propagation, and here there were situations in which the algorithms were propagation. And in this case, there is an additional situation where algebra enters, and that doesn't exist in this case. But he saw enough similarity that working with Feder-Vardi, they actually propose a common generalization. So the common generalization now is you have an arbitrary set and an arbitrary number of relations of arbitrariety. So H is a finite set, I still call them vertices, and there are a finite number of finitary relations. And then the input is another structure, G, which has similar relations. If this is ternary, then this is ternary, and so on. Same number, and preserves this one maps to that one, this one maps to this one, and so on. So the question is there an assignment that preserves all the relations? And so they conjectured that actually dichotomy holds for this more general context. There are situations in which the problem is polynomial, and all other situations the problem is empty-complete. Now, in the paper, the Feder-Vardi paper, this is also one of the very highly cited papers. he actually develops the techniques that play the role throughout the quest for dichotomy, which is kind of the analog of what Schaefer does. There are these problems where solution is trivial. There are the problems where the solution is obtained by propagation, and then there are problems that are different that seem to enter algebra. Now, maybe I'll have opportunity to say something more concrete about it, but I don't want to spend time on it right now. So this is the Feder-Vardi Conjecture, 1993. I just want to say that the constraint satisfaction aspect of it, that we call this constraint satisfaction, might sound strange to those of you who are in more AI-ish computer science, where constraint satisfaction problems are formulated differently. You have individual variables with their individual domains, and constraints talk about concrete tuples of variables, but it's all easy to see that they are equivalent. And there is another formalism in relational databases where you can talk about a relational database with a given vocabulary, and then each question is a query evaluation question. So for example, K coloring would be formulated as follows. The universe is elements 1 to K. The vocabulary, the relations you can use is distinctness. And then the query you are making, are there values V1 to Vn, so that for every edge of the graph, the values are different. And so this is a typical query evaluation in a relational database. So this is a general model that appears throughout computer science. All right, so now let's come back to Ladner's result, because he says the intermediate problems must exist, but we can ask, well, what are they? And this, if you are old enough, you might remember, has a checkered history. So in my memory, the first that everybody was talking about was linear programming, right? Linear programming is a very efficient algorithm, but it's provably not polynomial. There are provably exponential situations, but they're very rare. Well, of course, it turns out that this problem is in P, and this was discovered by Khachiyan with the ellipsoid method, and then Karmarkar, the interior methods, a few years later. Another problem like that was primality. Is this number prime? Now remember, polynomial time means polynomial in the length of the input, right? So the number is written in some system, and so it's the logarithm of the number is the length of number of digits. So it has to be polynomial in that. Well, that also turned out to be polynomial, and I think this has some Indian connection. You might remember, 2002. Another problem that's still out there as a possibly hope that this is a problem which is intermediate, neither polynomial nor NP-complete is graph isomorphism. Although, as you know, there was a big breakthrough by Latsi Babai, who proved a sub-exponential bound on it, so this kind of makes it unlikely that this would be NP-complete. Now, I had a similar experience, or I had some experience with this, because we studied, Feder and I studied a problem that we thought, oh, here is a problem that could actually be intermediate. It's really a neat problem, and I will describe it to you. So you have a complete graph whose edges are colored by 3 colors. And now you want to color the vertices also by 3 colors, so that you don't get an edge of color I, both of whose endpoints are also colored I. Now, this is kind of weird. Why am I choosing 3? But if you just do 2 colors, then you can think of them as edges and non-edges. And so what you want to do in this arbitrary graph is to color the vertices 1 and 2. 1 is a clique, and 2 is an independent set. So this is the problem of split graphs, when you talk about two, and there is a well-known polynomial algorithm for that. And it wasn't difficult to prove that with 4 colors this is NP-complete. So here is polynomial, here is NP-complete, this case is in between, maybe, who knows. So let me give you an example of a situation. So here is a complete graph colored by 3 colors. It's kind of hard to look at, so let's skip all the green edges and remember that non-adjacent means green. Let's try to color it. So I can say I cannot color both of these by red. But if I color one of them by blue, then I cannot color this one by blue. That's okay, but then I have the same problem on the other side. So I need at least 3 colors, right? I can color these 2 red. This cannot be blue. Sorry, I can color this red and this blue. Then this one cannot be blue. So it must be red if I only have 2 colors. Similarly, this would also be red, but then I have the problem with 2 reds. Right? So this needs at least 3 colors. If I have 2 of those, I need at least 4 colors, and so on. Anyway, similar idea, similar logic leads to an algorithm of order n power log n. So this is a prototype sub-exponential, not polynomial bound. And we couldn't improve this and couldn't improve this. This is 2006. Now I decided to talk about this problem here because something very nice happened. In 2010, these people showed the problem is polynomial. This is kind of Polish group of people interested in parameterized complexity. And they actually used techniques from parameterized complexity to prove that this problem is polynomial. The analysis was kind of typical of parameterized complexity. So this kind of says something about the maturity of the field. You've developed techniques that can be used to solve problems in another area, right? It's a very nice development. Anyway, so the answer is we still don't have a good problem which is of intermediate complexity. So you might take a different approach. You might say, let's try to think about areas where dichotomy holds, where there are no intermediate problems. And Lardner result says NP is too big. There are intermediate problems in that. We cannot take all that. So the rest of the slide here is in terms of descriptive complexity. And you might remember a fundamental result in descriptive complexity is a theorem of Fagin, who proved that NP can be described by existential second-order formulas. So any problem in NP can be described by a formula which is formula in which the second-order quantifiers, that those that apply to sets and relations, are only existential. For example, you can say, how would you describe 3-coloring? You would say there exists a set R for red, there exists a set B for blue, there is a set G for green, and now everything else you can describe in first-order logic. You can say every vertex is in at least one of them, no vertex is in 2 of them, no 2 in a set are adjacent, and so on. You write one long formula, and here is a problem that's in NP. And every problem that you can describe by such a formula is in NP. So it's a description of the class NP by a logic formula. And Feder and Vardi took this up and added 3 adjectives. I'm not going to define what they mean, but okay, A, B, and C. And they proved that if you describe a logic class by formulas that are A and B, then there are still intermediate problems in that class. If you take the class that are formulas, this is a subclass of NP, right? Those that have B and C, there are still intermediate problems. If you take A and C, there are still intermediate problems. But if you take A, B, and C, you get precisely the class of problems that are described by CSPs. So for any formula that uses monotone, monadic, and without inequality formulas, there is a structure H, so that those structures that satisfy the formula are precisely the structures that satisfy that are yes answer to the CSP. Okay, so in this sense, they argued that their conjecture kind of identifies the, in some sense, best possible or largest possible class of problems where dichotomy could hold. Beyond this, maybe there is no dichotomy. So this also contributed greatly to the popularity of the conjecture. All right, so the conjecture, to remind you, is that for every finite relational structure, the problem is NP-complete or polynomial. And they always kindly cite both the Schaeffer problem and our Schaeffer's paper and our paper as the motivations for this conjecture. Now, you notice that I only talked about undirected graphs. What would happen if we had a single binary relation, but not necessarily a symmetric one, just a digraph? The homomorphism problem for digraphs makes perfect sense, but it's a different kind of animal. Those problems are as hard as all of CSP. And in fact, Feder and Vardi proved that it's enough to prove the dichotomy conjecture for one binary relation, as long as you don't assume it's symmetric. So here graph theory comes and plays an important role already. I will hopefully, I don't know how I'm doing on time, but hopefully I will be describing one other deep connection to graph theory. But let's start first with noticing that Schaeffer solved this problem if the domain has two elements, right? So you might ask, what about three vertices? Now here I had an opposite experience from the one when Meshetchil visited me. Feder and I worked on this case for a long time, maybe not as long as the graph dichotomy, but devoted a lot of energy to this, and we had a system and we were kind of approaching the classification when Bulatov's paper came out, and all that hard work has gone down the drain. But this has been established. 4 vertices has been established. 5 vertices has been established. By now, the techniques that they developed, which I will mention next, were strong enough that eventually they were able to prove the conjecture, and this was independently by Bulatov and Zhuk in 2017. The solution of the conjecture is very appreciated because a lot of people were working on it in large effort in algebra, logic, and graph theory, and other parts of theoretical computer science. Big effort, lots of papers. This is, as I mentioned in the abstract, resulted in an award of the Alonzo Church Award of the European Association of Theoretical Computer Science in 2019, but it was given to Feder and Vardi for their foresight and formulation of the conjecture, not so much for these people whose solution involved so much, you know, all the joint effort. It would have been somewhat difficult maybe. They still should receive the high credit for solving the problem, of course. So, I want to say something about the other connection to graph theory, because that contributed greatly to the eventual solution. And that's the connection to list homomorphisms. Now, if you're here for the conference, you've already seen list homomorphisms and list colorings. This is a refinement of the homomorphism or coloring problem, where some vertices have images that are restricted. You can only map vertex V to one of the vertices on its list. And so you can ask for every fixed graph H, what is the complexity of this problem? Here what you are given is the graph G together with the lists, and you want to know whether there is a list homomorphism. This turned out to have a very nice answer. Let's start with the reflexive graphs. So this problem is polynomial time solvable if the fixed graph H is an interval graph. Vertices can be represented by intervals so that two vertices are adjacent if and only if the intervals intersect. There you can use the geometry to define a polynomial time algorithm. And it can be shown that in all other cases the problem is NP-complete. So there are similar, so this is proved by Feder and me in 1998. I like to remember this because invited me to Stanford and I stayed at a hotel in Palo Alto. This was the year of the, I guess must be at least a year or two earlier when we were working on this. This was the year of the soccer championship in the United States. And the hotel he put me in was the hotel where the Brazilian team was housed. So I had a fun time at that time, and I have a good memory of this paper. Well, similar dichotomy classifications have been proved for other context and list homomorphism problems. And eventually, was to zero in on pairs of vertices from the image. So in the graph H, you have a solution to these two vertices and a solution to these two vertices, and solutions to two vertices are kind of Schaefer. So you could use techniques and ideas from Schaefer to solve this problem. And that then played a similar role for the eventual solution of the entire. I'm going to skip this, because I want to say at least a little bit about where the algebra comes in, because algebra played a major role in this. And so it enters through polymorphisms. So we have a graph H, and the k-ary polymorphism is a homomorphism from the kth power of H to H. So for digraphs, what this means is if you have two vectors in the product that are coordinate-wise adjacent, then the images must be adjacent. If it's in such a relation, then the images must be in such a relation. So polymorphisms play an important role in the complexity of the homomorphism problem. If you have two structures that have exactly the same polymorphisms, then they are both NP-complete problems or both polynomial problems. And in fact, if you have a structure which has more polymorphisms, if H prime has more polymorphisms than H, then the homomorphism problem for H prime can be reduced to the homomorphism problem of H. These are a result of Javens and his collaborators and then students, including Bulatov and Krochin. And so let's remember this by saying that if a structure has few polymorphisms, then it's likely to be NP-complete, and if it has lots of polymorphisms, then it's likely to be polynomial. Now, the set of polymorphisms forms an algebra under composition, and studying that algebra turned out to be the important thing. It's not even important what the polymorphisms are, but what equations they satisfy in the algebra. And so this is how universal algebra came in and was applied with great success, eventually leading to the solution. How am I doing on time? I will mention a couple of polymorphisms that play the role. So the problems that are solved by local propagation algorithms correspond to two kinds of polymorphisms. One is semilattice, which is a binary polymorphism which satisfies commutativity, associativity, and is idempotent. And then the near unanimity polymorphism, which satisfies this equation over here. Then the algebraic problems usually typically satisfy, I'm simplifying greatly, typically satisfy these Maltsev equations, which are equations that x, y, y, and y, y, x give x. You can think about the, say, for linear equations modulo 2, you have a polymorphism that says x plus y minus z, right? Sorry, x minus z plus y, plus minus plus minus. And that satisfies this equation. The y's cancel because there's a minus here, the y's cancel because there's a minus here. Anyway, in Post's work in universal algebra, there was a polymorphism identified called weak near unanimity, which has the same kind of equation as this one. You only don't insist that the answer be x. All these values have to be the same. This turned out to be the key polymorphism, and in the result of Bulatov and Zhuk, and the conjecture that eventually, prior to their result, came to be, the distinction was the problems that admit a weak near unanimity are polynomial, and problems that don't admit that particular kind of polymorphism are NP-complete. This is how the conjecture was eventually solved. So, how about digraphs? Can we now answer which digraphs give polynomial problems and which digraphs have NP-complete problems? There's a nice answer for smooth digraphs. This is a name we invented for digraphs that don't have sources or sinks. Every vertex has at least one incoming edge and at least one outgoing edge. Bang Jensen and I conjectured that only problems that are equivalent to a directed cycle are polynomial. Everything else is NP-complete. This seems a natural conjecture because it would generalize the dichotomy for undirected graphs, because in undirected graphs the only cycles possible are length 1 or 2, which means a loop or an edge, bipartite graph. Well, this was eventually proved by Bartow, Kozik, and Niven in 2009. But for general diagrams, we still don't have a nice answer. Here is an example of a tree for which the homomorphism problem is NP-complete. But if you change the length of the paths just a little bit, it becomes polynomial. All right, so let me close by mentioning this profusion of generalizations, extensions, and related results that has come to pass since then, and I guess each of them would deserve to have a lecture of its own. You can have weights on edges, and you can talk about homomorphisms costing things, and you want to talk about minimum cost homomorphism. There, a dichotomy has been accomplished. You can talk about signed graphs where edges have signs, plus and minus, and before you map G to H, you can switch at a vertex, change all pluses to minuses and all minuses to pluses. And then you're looking for a mapping that preserves pluses and minuses as well as edges. So the dichotomy there was proved by Brewster and Siggers, but the list dichotomy is still open. In fact, one of the problems we are working on. You can ask about surjective homomorphisms. You don't just want an arbitrary homomorphism, but you want one that's onto vertices or edges. Vikas was my Indian PhD student some 10 years ago, and he is in Pune. If you are from Pune, you can talk to Vikas about the current state of surjective homomorphisms. The dichotomy is open. It seems very difficult. Similar about retractions. Much has been accomplished for list homomorphisms where we refine the complexity. Those that are polynomial, we divide to those that are solvable in log space or log space complete. And so there are trichotomy results. There is a lot of work about counting homomorphisms, Dyer and Greenhill. Fouquet, Goldberg, and Givney are now working on counting homomorphisms modulo a prime. It's also a nice dichotomy in certain cases. They're quantified CSP, valued CSPs, promised CSPs, and so on. And it's also nice results on restricting the inputs. So maybe, like Karthik's lecture, you can forbid an induced path. And actually there are interesting results on this by Seymour and Scott and others. And I think I ran out of voice, if not time, so I will stop here. Thank you.
So it was a nice lecture. So I have a question regarding the core of a graph.
Regarding?
Core of a graph. C-O-R-E, core of a graph. Whether the graph is core or not.
Chordal.
Core means...
Okay, continue. I hear badly, so I will maybe conclude from what you are asking.
Maybe you have introduced the core of a graph.
Core, I see. When the graph is a core.
Yeah, exactly.
Okay, sorry, I hear you.
Yeah, so whether it is to determine the graph is core or not, is it an NP-complete problem or... Because it depends on the homomorphism, like endomorphisms of a graph.
Is the graph core is an NP-complete problem?
Yes. Yeah.
When we are talking about these complexity problems, of course, if two graphs are homomorphically equivalent, there is a homomorphism both ways, then we can just talk about one of them. So often we assume that the graph is a core, and that has important implications by basically allowing constants as additional relations, so that I can talk about if there is a homomorphism, then it's a homomorphism onto the core.
Okay.
So, but you have a different reason to ask, yes?
Yeah, I mean, because it depends on if the endomorphisms are automorphisms, then it is the core.
Yes.
So that's why if the homomorphism problem is NP-complete, right?
Yes.
So it depends on that. So maybe it is also the NP-complete. That's what my question was.
Whether it's NP-complete for isomorphism?
To determine whether the graph is core or not.
Oh, I don't remember what the proof is offhand, sorry. But I do remember that we proved in one of the earlier papers, Vidnesh et al., that to decide if a given graph is a core is NP-complete.
Okay.
I don't know whether what you're proposing is the proof. I think the proof wasn't difficult, but it wasn't a one-liner.
Okay, so it's better to go through that paper which you have introduced.
Yeah.
Okay, thank you.
All right. Speak slowly.
With the use of these algebraic techniques, now if you go back to the logical characterizations, do the monodic or monotone formulas correspond to some polymorphisms and some nice structure?
You want me to go back to that slide?
No, you don't have to. No, I'm just saying that do these polymorphisms correspond naturally to some logical definable classes, like, because they were talking about it in terms of inequality or monodic formulas or monadic formulas or monotone formulas.
It's a good question. So I don't know a connection of the descriptive complexity to the polymorphisms, but I suspect that it's true. You must be right, and they probably have studied it. My experience with the polymorphisms is from the graph theory side, and that is a nice experience. The polymorphisms for graphs have some bearing to structured graphs. Just like the existence of certain polymorphisms is like the existence of representation by intervals or an ordering characterization. And so if you remember the list homomorphism problem I described that gave rise to interval graphs, there is somehow the polymorphisms for that problem are the geometric representation for that problem and the solvability of that problem in polynomial time that form a logic triangle. And we know the solvability is equivalent to the geometric representation. We know the solvability is equivalent to the existence of a certain kind of polymorphism. So it's that polymorphism that describes the geometric representation. That's kind of typical for polymorphisms corresponding to list homomorphism problems. They are called conservative polymorphisms. The answer is always one of the arguments. And so I think for graph theory, the biggest takeaway from polymorphisms is in this conservative context, because all these useful algebraic polymorphisms define nice graph and digraph classes. This is a little bit also behind what my first lecture was about, the graphs with possible loops, because we kind of saw the similarity of the problems that I was describing as similar because they have the same polymorphisms. So I think that some future time you study classes corresponding to each of those individual polymorphisms.